here's a recap of what we did today in the bicycle problem. Still a bit more to do, but I want to make sure everybody's up to speed to do some problems of a similar vein for tonight. So we've got a bicycle. We're turning the pedal. That's cranking around. That's turning the front gear. That pulls the chain. That turns the rear gear. And that makes the wheel go around. And we made some measurements, such as the radius of the front gear. There's more official names for that than front gear and rear gear, but I'll just use front gear and rear gear. Front gear, 8.5 centimeters. Rear gear, 5.5 centimeters. Radius of the rear wheel was 37 centimeters. And we assumed that we were pedaling at 2 revolutions per second. The pedals. Remember, that's how fast your feet go around. It's not directly how fast the rear wheel goes around. That's actually way down here. And so we want to know what's going on. Well, there's some shortcuts that we're going to see that are not as laborious as writing all this stuff down, but I think it's really good to write all this stuff down to get practice with these ideas of linear and rotational motion. And so the idea is just look at all the different parts of the bike that we think are relevant and how fast are they going. And remember that there's 2 versions of what how fast means. If it's some rotating object, then it makes sense to talk about revolutions per second. And soon, I'm going to just put a little advertisement, soon we're going to get yet another way of talking about rotational speed, which turns out to be very, very handy. But then there's also, if I have a specific point that I'm interested in on some object that's rotating, like the pedal or like the teeth of a gear, then I can actually think about, okay, that's just a point moving in space. How many centimeters per second is it going? So when I say turning here, I'm trying to suggest turning, how fast is it turning? That's going to be in terms of revolutions per second. So I'm going to write in the units right now. Moving, that's supposed to suggest linear motion. So that's going to be, for us, centimeters per second. You know what? It's going to probably take up less space if I do this. Revolutions per second. Okay. And so this guy is going to be centimeters per second. This guy is going to, let's see, this guy also centimeters per second, centimeters per second, centimeters per second. And then these guys, whenever it says turning, we're going to do revolutions per second. Okay. So that's really important to get that clear. So we have the pedal and the front gear. We know how fast the pedal is turning around, 2 revolutions every second. Every second we see this pedal just go around twice. Well, how fast does the front gear turn around? The crucial thing is it's the same, because it's part of just one fixed rotating object. It's not deforming. The pedal's not racing ahead of the gear. They're fixed together. They're part of one rotating object, one rigid body, and so this is going to be the same number. And that's really important. When you have 2 pieces of the same rigidly rotating object, they're all rotating at the same revolutions per second, the same rotational speed. That does not mean the linear speed is the same. Now, how fast are the teeth of the front gear moving? Specifically, that outer edge of the front gear that's pulling the chain, there is where we have to convert to centimeters per second. Okay, so we were thinking about that before. We take the revolutions per second, the rotational speed, okay, and then we multiply it by how many centimeters per revolution. And how many centimeters do we get? Does it move per revolution? It's just exactly the circumference of the circle. And so that's going to be 2 pi times the 8.5 centimeters for the radius. And let's go down and do some scratch work here. So we get 2 times that conversion factor of 2 pi times, I don't really need the bar, do I? 2 pi times 8.5. And that's 106.81. A lot of people are getting that number. 106.81. Okay. Now, how fast is the chain moving? Let's go back to the picture. So a particular tooth of this wheel is going around, and if I just look at a snapshot and just in a 1 microsecond or something, I look at it move, and I look at its speed as it's moving, the teeth of the gear, They're moving at 106.81 centimeters per second. Well, they're latched onto the chain. That's what makes the chain go around, is the teeth engage the chain. So any point on that chain is moving at the same linear speed. They're not slipping. And we talked about this a little bit outside, I guess on Friday, how if two things are glued together like that, just like the wheel and the road, they don't slip on each other, we're going to have the same linear speed. So this is really, really crucial. It's probably the biggest part that I think people get confused about. The chain is what's driving this whole thing. Without a chain, there wouldn't be any bike. The pedaling wouldn't do much to make the bike move. And the chain is the link between these things. And the fact that the linear speed is the same is crucial. Now, how fast are the teeth of the rear gear moving? Same exact argument. They're sort of glued temporarily to the chain, and so that's 106.81. So why isn't everything just the same number? It's because we're going to convert that back to rotational motion. We don't care really directly how much the chain is moving. That's just an intermediate quantity. But we care, what does that do to move the wheel? Why is the tire moving? It's because the whole wheel is moving, and it's because this back gear is moving. And it's because it's turning in particular. We need to know how many revolutions per second that goes around. So we're going to convert back to the rotational world. Well, now we have to go, we just have to do that in reverse. So we take 106.81 centimeters per second. Okay. Now we have to do the reverse of this conversion. So 1 revolution, okay, to get revolutions per second out, we've got to take that, and that's going to be 2 pi, let's put that in math mode, 2 pi times 5.5 centimeters. Because now we're talking about a different wheel. How fast is the rear gear? We're converting from the motion of the teeth of the rear gear to the rear gear itself in terms of turning. Okay, so let's go back to our scratch. And we've got 106.81, and we're dividing by a circumference, which is 2 pi r, which is 5.5. And let's not overdo it. Let's compute it. 3.09. Okay, and so that's 3.09. Alrighty, so now instead of the 2 revolutions per second we had of the pedals, we see that the rear gear is moving at a different rate. But now the rear gear, that's the same rotating object as the rear wheel. They're all turning together. If you looked at while we were spinning the crank on the bike, you could see that this rear thing just goes around. It's as if it's one fixed object that's all rotating together. So this is the same as this. Notice how many of the numbers here are the same. There's only 3 numbers so far, even though I've got like 7 different slots. Okay. Now how fast is the outer edge of the rear tire moving? That's centimeters per second. We want to get eventually the speed of the bike. And we figured out on Friday that if we could turn the bike upside down and figure out how fast a thorn on the tire is moving, that's going to be the same as this number of how fast the bike goes. So we have to convert again. 3.09 revolutions per second. And so now we're converting, but with a different radius. Now we finally use the 37. So we have 37, 2 pi times 37 centimeters per revolution. And that's going to give us, the revolutions are going to cancel, and we're going to get centimeters per second. So now 3.09 times 2 pi times 37. In fact, I'll just use this number here. Let's see. 3 times 2 pi times 37. Boom. 718.54. Cool. Okay. And that's how fast a point on the outer edge of the tire is moving. How fast will the bike go if all this happens when it's not upside down and the seat and the handlebars are tied to something, but when it's actually allowed to move, it's the same exact speed. And we figured out how fast the bike goes. That's a lot of different things to write down, but the key was that every step was either the same number or just multiplying, dividing by 2 pi r, a circumference. And we're going to be able to figure out a shortcut here. And it's good to look at this and see, is there something I can kind of shortcut from, in particular, from this 2 to this 3.09. And definitely some people were already looking into that. Okay, that's good. And then the homework's going to be doing a version of this.